Okay, so we have, if we remember some videos ago, we have the three-dimensional optimization. We just have a few homework problems at the end that we didn't do. It's probably going to take a few videos to get into that, but there's a lot of small ideas. That's what's kind of hard, the nitty-gritty details. There's a bunch of it's not that hard. There's just a lot of small ideas within the optimization section. And all of this, even though we've done some of it, all of this is also leading into three ideas. We'll get there. One is the Cobb-Douglas that we know. The other one is the kind of the level curves of that plane, and then the new one is like the L curves. So there are three very common graphs throughout this course here. But a lot of we just want to kind of go through the textbook. A lot of the very elegant wording here, like this first paragraph in economics, they discuss some of the ideas, but some of it we'll kind of read through. Other stuff will kind of pass, but it's just it'll answer itself when it gets there. There's a lot of small little math ideas, warming up to how we optimize these different graphs and functions. But it's better we just start because it takes a lot of time talking. So we start optimization. We're going to quick go into multivariable optimization. They do a quick review of two-dimensional, which is our calculus one. Uh, the odd thing throughout this, it's kind of a contradiction. For this class, we only need calculus one, not calculus three, but every single idea in here is from calculus three, not calculus one. So we're learning some of the most elementary calculus three in this book. We do need calculus three. It just, we have to learn it as we go along here. So the descriptions here are not important, but we are supposed to kind of understand these idealisms. In many economic applications, people need to make choices. For example, a consumer needs to choose how many units of a product she wants to purchase, while the CEO of a firm must decide how many units of a product the firm should produce. A running assumption in this book will be that people try to make optimal choices given what is feasible for them to do and given the information available to them. We will construct models to represent the choices available to these individuals, and we will solve these models to find the optimal choice that they should select. In other words, the individual must choose one option X from a set X, and this independent variable X affects some other dependent variable Y according to some function F. Yeah, the individual might want to choose X that maximizes or minimizes Y, depending on the variables of interest. For example, if Y represents profits, then a CEO wants to maximize Y. If Y represents a production cost, then the CEO wants to minimize it. In upper level economic classes and in other fields such as engineering, you may encounter very complicated optimization problems. In this book, we will mostly work with simpler optimization problems. Therefore, in this section, we focus on the fundamental tools you need to solve our problems, and we will mostly overlook technical details like first order condition, second order condition. We're about to get into the fact that that's not important. But therefore, in this section, we focus on fundamental tools you need to solve our problems, and we will mostly overlook technical details that are only relevant to more complex problems. For instance, we will mostly consider applications in which the second order conditions are satisfied. Thus, we do not need to spend too much time on this topic. So unconstrained problems. Unconstrained just means that we don't have any restrictions in our domain. If we look at all these graphs here, these four graphs, they're two-dimensional graphs. Yeah, this is a single variable calculus. So we just kind of skip this. It kind of describes the math in there, which we don't want to do. We notice some very obvious things. I don't think we get a whole lot of this in this class, but here we have a slope of 0, and it's not a max or a min. Of course, you have that, but that they only put that there to kind of show something that's not important in the class here. So we know parabolas either have a max or a min, yes. And we might have what's called a local max, and the absolute min or max is the highest point. So we have an absolute min here. We have Absolute minimum, we don't have an absolute maximum, not if the domain is a negative infinity to infinity. So we're supposed to know all these small details from Calculus 1, but the problems in this book are simple enough, and they basically have a set of instructions to optimize, yeah, the three graphs, the Cobb-Douglas, the other one, which is more linear, and the third one, which we haven't covered, which we're kind of warming up to. They're just basically showing us pictures from Calculus 1. We don't have to describe these. All the nitty gritty details of maximizing, we just don't really need them. So we don't care about this. We're just going to kind of read on here. This is figure 2.7. They might mention it later. Uh, but they're just saying this marginal principle is just take the derivative and set it equal to 0. So it's not engineering, it's econ. They give it its own special name. It's freakishly easy. Marginal principle just means take the derivative, set it equal to 0. That's all that means, which is what we've done through all calculus 1. Yeah, in economics, we refer to this as the marginal principle. It simply states that the value of the marginal function is 0 at any extremum, maximum or minimum of the function. This principle can be extended to state that if a point x, this principle can be extended to state that if at a point x we have the derivative greater than 0, then in a neighborhood of x we should raise x if we are interested in maximizing y, and we should lower x if we're interested in minimizing y. So we read all this stuff that we don't really understand when we read it. But literally, if we kind of closely go through all of this, they're literally talking about on purpose a basic review that we should know, but we don't usually we don't use a lot of it analytically in this class. So the most basic thing from calculus 1 is take the derivative, set it equal to 0. Second order condition, first order condition. We know if something is at a top or a bottom. I mean, you can always just plug it back into the function. We can kind of skip all of this here. It doesn't matter. Okay, so it gets really funky and fancy in constrained problems. This is it in a nutshell. I have to read closely. If we don't read closely, we don't quite understand what it means, but it doesn't matter. A constraint just means that we assign it a domain now, you know? So we make up a problem. If we have a parabola like this, obviously it has a min anyways, but it could be limited, you know, to a domain right here. The constraints are a little bit more fancy when it comes to three-dimensional problems, which they are. But a constrained maximization problem just means that we have constraints. It means you have an equation in domains that we have to pay attention to. The equation is the constraint. Yeah. We're just doing a short introduction. Let's kind of do the constraint in the next problem here.